bit more about concepts, prerequisites, routing versus forwarding, again, routing schemes, basic concepts for routing, fundamental routing algorithms, so a bit more background so that you better understand how those well-known protocols like OSPF and BGP work and why they work the way and what the problems are. Okay, what do we need? Basic concepts, prerequisites. Well, first of all the places need unique names. Well, I mean, if you go through, like going through a maze here, well, you have to know where to go. So here, you have to be sure all the nodes have their IP address. At least one, we can have more than one. That's no problem. And for routing in the internet, it must be a routable address, a global unique address. So we cannot do routing with link local or private addresses. Link local, remember, IP version 6, private addresses in IP in general. So in version 4 for most of the home users, you have this 192, 168 dot, etc. These addresses. So they cannot be used for routing. So for global communication, we need the global unique IP addresses. So, okay, prerequisites, very simple. Then back to routing and forwarding. Please don't confuse these terms. We already looked into routing table and forwarding table. Even more, forwarding, we saw this is really where the router picks. Now for this incoming packet, the outgoing port, forwarding is a pure local process running on this very single computer. So incoming packet moved from input interface to the appropriate output interface. That's it. Very local process. Routing, creating the routing table, it's a distributed process. And there's a lot of cooperation with many different devices and network, all the routers. Well, not all for all the steps, but in the end, yes, it's a distributed approach towards this finding the set of whatever optimal paths. So we monitor the traffic, we exchange parts of the network topology, and the idea is then to allow correct forwarding decisions then locally on the router. So routing and forwarding, different things. And as I showed you already, don't confuse routing table and forwarding tables. So yes, we have them as data sets on all the routers, but again, the forwarding table is the product of the routing process. So we derive from all this topology information, in the end, the forwarding table. That's the idea. So in this setting, we do all this exchange of routing information, we'll see, with help of routing protocols. We apply certain algorithms that will find optimum paths, etc. And at the end, we will create our forwarding table. So that is the idea. This is where we need our nanosecond quick lookup. The routing table itself, that is our raw information we get in. This basically formed after, powering up of a router. Then you create the routing table and then you fill information in the routing table. And it really depends on the routing scheme. We'll see examples for this. And there are even some simple routing schemes operating without any routing table. They only have a very simple, maybe even a simple forwarding table. Think of flooding. You have only one very simple forwarding principle, flooding. If a packet comes in, flood it to all other outgoing ports. Very simple. You don't need any routing table. You only have this very simple forwarding, table. Maybe you can call it a table. So if something goes in, forward it to all outgoing ports. So routing tables, forwarding tables, we saw already in the last subsection some examples. Okay, what do we do? Forwarding, the forwarding scheme, basically, as I said, moves the packets from input to the appropriate output, simply based on the forwarding table. It has to be extremely scalable well, you have to be able to look up these entries in a very fast, efficient way, and this is where we really need efficient, sophisticated data structure. So basically, what you can do is, in a very simple way describing our forwarding table, it's a very simple key. You have a destination address. So there's a destination address A, and you know if the address is A, then the output is port 13, for example. And if it's B, then it's maybe also 13, but if it's C, then it's 47, and whatever the output is. So you could create forwarding tables only based on destination addresses. This is something you also do in the postal service. I mean, if you have a parcel or a letter, whatever, you don't look at the sender address, only at the receiver address. So very, very simple. So very simple forwarding here. You could also think of looking at source and destination. So this is, for example, interesting if you say, okay, if you have a special source, everything that comes from A and goes to X, you use the output 17, but if it's from B and goes to X, that's a customer that doesn't pay that much, you take the output 18. You could do things like this. Most common case, you look only at the destination. And how you do it, concrete implementation, well, that's based on the longest prefix match. Longest prefix match, that's typically used in the internet. So we have prefixes, network prefixes of addresses, shorter prefixes or longer ones, and then you look if there's an incoming packet that has a certain address. Let's call the address AXY. Then you check for the longest prefix match. It's this one, and then the output is interface 2. If you have a packet that starts with ABX whatever, then you have this, assuming this would, well, A and B means simply, for example, bits and bytes from the addresses. So that's the idea. You can also do something else. Longest prefix match, as I said, that's the way internet routers do this. You could also give certain packets labels and then perform an exact label matching. So this is a technology we will briefly touch when I mention multi-protocol label switching, a technology to manage traffic in the internet. But the peak days of MPLS are also over. So exact label matching, that means that you label traffic streams. And I say, okay, traffic stream 4711, that always takes this and that, and you set up, during some kind of a connection setup phase, you set up a connection across the network and you label traffic streams that then follow those, well, path along these labels. We will more focus on this longest prefix match, the internet style of forwarding packets. Okay, so what is the idea of looking into to not only destination but also the source? As I said, you may want to differ the forwarding towards the same destination based on the source. Maybe you know that this router, yes, this is maybe a faster way, but it's more expensive compared to this one. And you have the orange customer paying more. Then if you look at this router at source and destination, then you can separate the traffic stream, although they have the same destination. If you only look at the destination, so our postal service only looks at the destination, then those two traffic streams will come together here at this router because they have the same destination. Okay, we are at basic principles. And you see there are many different ways how you can do this, and I will always tell you what is the typical way of doing it for the internet. There are also other network types that may do it in a different way. But typically, a lot of the traffic is handled this way, that you look at the destination, not at the source, and then the traffic flows come together. What else can we do? We can create probabilistic forwarding. Could be deterministic. It could be also probabilistic. What is the difference? Well, not the routing, now forwarding. So we have a forwarding table, and typically, and these are the examples I showed you so far, we do deterministic forwarding. So for example, longest prefix match. We could, if we want, also add some randomness. Why? Well, for example, you could say, yes, to this destination A, half of the traffic flows this way, half of the traffic flows that way. This can be done for load balancing. So if you have two alternative ways, paths, then you can pick one out of them. You can also prefer one of the paths. So maybe you know that in the second row that I3 has a higher capacity, then you can actually map 70% of the traffic to I3, interface 3, and 30% to interface 1. So you can assign certain randomness to the decision of the forwarding. So you can do different things to forwarding. We will not focus here on forwarding anymore. They are not distributed, and we more focus on routing. So yes, the size of forwarding table is extremely important. We have memory constraints. This has to be handled in hardware extremely fast, but this is a local process, and that's more implementation issue, and you can do things like adding some randomness to the process. We will more focus on routing because this is where you have all the clever algorithms coming in, all the path selection, the policies, this distributed approach, these different domains, administration, more complex compared to forwarding. Okay, so routing. Routing, as I said, is the process that leads, in the end, creates some end result that fills the forwarding table. So that's more control plane. What does it mean? The routing is based on a control flow of data between different routers with the help of routing protocols. Then you have a routing algorithm that computes certain content, and then in the end you fill the routing table and derive from that your forwarding table. Forwarding itself, the fast one, that's always on the data plane. Data plane, that's basically the part of our network that handles the user data, the huge amount of user data. Control flow should be just a little bit of data, just some megabits per second, not the terabits per second. So data plane, pure hardware, extremely fast, forwarding tables, the forwarding mechanisms. The routers also have a control plane, and this is with the help of the control plane, they exchange their routing data with the help of routing protocols. So this is a second layer, so to say. So control layer and the real data layer. So again, control plane is needed to control the forwarding of the data. So control plane is important for computing the paths all the packets will follow, and also the control plane will then actually take the routing data, fill our forwarding table, and the forwarding table then will actually handle this nanosecond forwarding of the user data. Yes, we also exchange control data, but that's rather in a time scale of milliseconds. That's for routing. That's something we do network-wide exchange of this data, well, depending on the routing protocol. Forwarding is all local scope. So very simple. So control plane, in the end, controls what the data plane does. And the really fast stuff, that's our real user data handling. And the slower stuff, that's this exchange of some routing information. So once more, what is the difference between routing and forwarding? What is the time critical one and what is typically done in hardware? And think of these ideas of destination-based routing only and source and destination-based routing. When could this be of interest? Do you have an example? Maybe also from the postal service, an example where also the source is important.